The collected materials are sorted by students, and you can see here manually dismantling them and separating the various components so that they can be shredded to smaller sizes for eventual recovery. The process is manual in its nature, where we're using various hand tools and such to separate. In this particular case, the primary components would be circuit boards in the lower right, and in the upper left, the ferrous metals, which could be directly marketed. The circuit boards are then shredded in this hard drive shredder. Now, we have two different stages, and this is a continuous process where we would, and it discharges on a conveyor belt. And you can see that the first pass is quite coarse, but multiple passes can produce a material that is quite fine. This is about 1/4 of an inch, which is the size that we intend to shred to. And in between these steps, we'll actually screen them using a vibrating screen in order to make sure that we don't produce too many excessive fines. This is a knife mill, a shredder, which is used for softer materials such as wire. It does an excellent job of stripping the insulation off of the wire. We would take power cords and cables and such, and after shredding them with the hard drive shredder, get them to this size, which you can see on the left, the wire, and the upgraded material on the far right, which are then separated by this electrostatic separator. So we feed the shredded material onto the separator, which is going to separate components based upon their conductive properties. And again, this is a continuous process. The insulator material retains its charge, and the conducting material actually loses its charge as it's conducted to the rotating drum, the grounded drum. And they're separated at the bottom into these various components. And here you can see an example of the after one pass, a pretty good job of separating the insulation from the wire itself. Multiple passes can produce a higher grade material, which could then be directly marketed. The components then go to electrowinning and leaching. This is our picture of our electrowinning cell, and the plated copper shown on the right. What we do with the material is actually put it into solution by using an ammonia solution to generate an oxidizer. We oxidize the components, and then we can plate copper directly onto the electrowinning cell cathode using electroplating technology.
The research that we do often makes it directly into the classroom, but sometimes while you're teaching, you still need a helping hand. It's important that we teach not only the people, but the machines that the people are going to be working with. Behind the scenes of all of this automation work, there's a lot of changes that need to be made to these machines in order to make them work in a mining environment. Many mining machines are far too large to fit in the laboratories that we have on campus, or they require too much power. So we have here a model of an underground shuttle car that we have operating in fully autonomous mode. This is the small version. It's a 1:6 model of a full-scale version that we have out at a mine site. You can see the shuttle car is navigating its way through the maze that we've created for it. It's trying to find some various targets that are placed in the maze that would be part of a regular machine operation. Working like this and in our labs allows students to interact with this machine in a way that they wouldn't be able to if we had to do all of this work out in the field. You can see here a close-up of the sensor package that's on the shuttle car. It's using a combination of LiDAR, IMUs, and various other sensors in order to tell its actual location. This gives students a chance to actually work with several different technologies. This particular project uses 18 different programming languages, as well as a wide variety of sensor technology. We take on the challenge of making existing machines work with new machines and integration of the two.